系统的角度写。
对，就是把进入那边抓过来，看到怎么发落这方面去。
对啊，好，老师是从哪边开始？然后老师笔可以用。OK， 好。在这里。已经开始录了吗？对，都开始录了。对，好。声音也出去了。应该等一下。这你们看一看，声音有没有出去？诶，发什么？有。我说声音有没有出去？用这个，不然用那个笔。
然后不用这个。所以不要用这个。
用这个的话，就是外面看不到。
好，那我把它拔掉。那我下次看要不要带那个滑鼠来。要吗？
哦，对了，滑鼠对，有那种无线的滑鼠是吧？
目前应该没有。
对啊。
这实验室就是可能要搬一下。
好，下次看看。
那个就是台积电那个人说要来演讲，那我们那个 PDF 就是直接交给系办处理。
对。
就直接拿给他们。
对。Okay. Last week we stopped here. Okay, we are discussing the message passing, and we say the primitive or operation supported by system for doing this message passing. Usually they have two types of semantic. One is blocking semantic, another one is non-blocking semantic. Okay, and this semantics they may be used for either the send operation or receive operation. Okay, and here we will discuss what is the blocking and non-blocking send. What the semantic of this. Okay, for blocking send, it's more natural for most of the programmer. Okay, because when you use this send request or send operation, you expect when the code for send return, that means the message is already delivered to the receiver. Okay. So the semantic for blocking send usually means naturally is coincides with this natural intuition. Okay. So the actual operation is something like that. Right? When the user sender using the blocking send, after issue this send request, the operating system or kernel will take over. Okay? And the sender will block there until the message is delivered to the receiver side. And also, in most cases, the acknowledgement also came back to the sender. Then the sender side kernel will unblock or resume the sender. Okay, so sender after return from the kernel or return from the send operation, they can continue their operation. That's the so most of our intuitive system code or API for the sends, the more convenient way or natural way is this blocking send, because when you return, you get return back from the send request. You assume the message is delivered. Okay, so the blocking send usually have this semantic. Okay, the non-blocking means that if the sender have other things to do, Okay, you don't want to wait later until the message was delivered. Okay, you can check that later to see the message was delivered or not. Okay, but in the meantime, the sender may have other activity. Okay, so for concurrent applications, so an application which has multiple execution flow coexisted, then this non-broken send semantic or non-broken send API may be much proper for this kind of application. Okay, and the semantic usually is like this: when sender issue a send which is non-broken, then the operating system will prepare. Okay, in general, they will copy the message content to kernel buffer, and then they immediately return. Okay. So sender only block during this message data copy from sender's user address space to kernel's buffer. Okay, and sender then can continue its operation. Okay, and during this return, because if the send operation is not blocked, then the sender should aware that only means operating system knows, or the underlying network system aware that or prepare to carry out the subsequent send operations. Okay, then and now become the sender's responsibility to find out either this message is actually delivered or when and so on. Okay, because the message, the data, the message is already in network or operating system's kernel buffer, and then the operating system and the network system will try to make sure this message eventually be delivered to the receiver side. Okay, and for this kind of there's some requirement or some characteristic of this kind of operating system. If they support this non-broken send, they need to have some special mechanism. So later the sender can try to find out the message was delivered safely or successfully or not. Okay. So the broken sender wait until the message is sent. Disadvantage is you cannot do other activity. You need to block there. But in the meantime, that's its advantage also, because the semantic is very clear. When you return, you know the message is delivered. Okay. But for non-broken send, the call can be returned to the sender immediately. But you are not sure when the message will be delivered, or it will be delivered successful or not. Later, sender need to find out itself. Okay, so buffer must be used in the kernel in the kernel space, and to keep the message there. Okay, and those buffer space you also need to be protected. Okay, because you need to be protected until the message is successfully delivered to the receiver. Okay, otherwise the message will get lost. Okay, and some mechanism need to be used to inform sender that the message eventually is delivered. Okay, either by interrupt, okay, or by polling. Okay, depends on what kind of mechanism the network system would like to support. Okay, for interrupt, if system using the interrupt, then the sender need to prepare an interrupt handling routine for this kind of interrupt, to catch this interrupt when this issue non-broken send. Then before that, they need to prepare an interrupt service routine, interrupt handling routine. So when this message delivered, successful deliver or unsuccessful deliver interrupt, it happen, the sender will know how to handle that. Okay, and of course, other ways that you using the polling mechanism. Okay, but either way, we need to copy, most of the implementation, they copy the message body from the sender's user space to kernel buffer, okay, and then usually mark those buffer as read-only, so they cannot be either. Remember, operating system, most modern operating system, they use virtual memory management system. So the physical memory may be replaced by something else, okay, or whatever. But of course, in the buffer, in the system buffer, they will not be replaced. But anyway, you need to make sure nobody will try to update those part of the memory, okay. And so if someone want to update, then you need to perform something like copy or write, or you suspend those updates until this part of the buffer become available. Okay. Usually until the message was deleted or was delivered and so on. Okay. So the possible implementation for the network system or operating system, they need to make sure this happens. Okay. So in general, blocking code is much convenient, okay, because the application programmer, they don't need to do anything else. They just block there, okay. And especially if your system support multi-threaded, then you can create a thread block layer waiting for the message to deliver. And in the meantime, you use other thread to continue to doing other activity, and okay, and this blocking thread will not affect other threads continue their works. Okay, so if a system support multi-threaded programming, then usually we would prefer using the blocking set because it's very easy to management. Okay. And for receiver side, it's similar. Okay, your system can support blocking receive or non-blocking receive as well. Okay, the blocking receive is that the caller will block there until the desired, expected message arrive and return to the receiver, to the caller. Okay, so again, it's good for multi-threaded system. So you just create thread block layer to waiting for the message. Then other thread can continue doing other things. Okay. For non-blocking receive, the semantic something like that. The caller will tell the kernel, the receiver, the caller need to prepare a buffer to capture the arriving messages. Okay, so they do need to specify there's a buffer space there is allocated for this particular purpose. Okay, and then the system will immediately return, and the receiver can do other things. Okay, so we need to way to tell eventually later to tell receiver the message already arrived. The reason receiver try to receive a message, that means the received information has some use, is useful for its application, right? So when the message arrives, receiver need to be notified, and they can use the arrived message to do it for its purpose. Okay, so there are these four possible mechanisms in general are used for this non-blocking receive. Either same as before, interrupt may be used. Okay, again, the receiver, if interrupt was used, then the receiver need to prepare an interrupt handling routine before they call this non-blocking receive. Okay, so when the message arrives, this interrupt handling routine will be triggered and then doing the work for capture this message. Okay, and also another way is using polling, so the receiver can poll the status of the buffer, okay, periodic, to find out the message arrived or not. Okay, and so for this kind of mechanism, usually we have two interfaces. One is poll to check the status. Okay, and if the status is changed, the message arrived, then you can use this get message to retrieve the content of the message. Okay, because in general this buffer depends on the semantic. Okay, if the buffer is in user space, receivers user, then you don't need to get message. You just use your variable or whatever data structure, and it's all right. Okay, but if the buffer is specified, is allocated in kernel space, then you need to use this to copy the message content to users addressing space. Okay. Another way is using a pop-up thread. Okay. So instead, it's very similar to interrupt. Okay, but for some multi-threaded system, okay, they can use in this event-driven mechanism. So when an event happens, so they treat this interrupt, they separate or categorize interrupt depends on their types, okay, or they classify interrupt into several types. Some events they treat, for example, this kind of application dependent events. Okay, then you can use instead of using interrupt handling routine, they use event driven routine. It's similar, but you call event driven. Okay, so for example, in Windows programming or X Windows or either Microsoft Windows, you have a lot of event driven event routines. You can specify that. So when you click something, for example, you move your cursor, you click a button and so on, it generates an event. Okay, and those are this kind of type. Okay, so they treat this receiving message or message arriving as a special event. Okay, and you design a pop-up thread. So when the event comes, you create a new thread to handle that particular message. Okay. So the advantage for this one is that, okay, the thread is similar to using the multi-thread mechanism. You create a thread, and this thread call is blocking receive block there. Okay, and here instead of create a thread beforehand, you wait until the message actually arrives. Then system create a thread for you to handle. It's similar, okay, but you delay the thread creation until the message arrives. Okay. So last one is the some system they support this mechanism. We call it active message. That means the message body actually contain a routine which can be executed in the receiver side. Okay. So handling message actually by this active message itself, okay, is similar to Java applet. Okay. When you receive an HTML document which contains an executable code, okay, so it can be executed in your browser. Okay. It's similar like this. So this mechanism can also be used in non-broken receive. Okay. So but by using this mechanism, usually you need to have this. The sender and receiver, they need to be in a completely trusted environment. So otherwise, it's very dangerous. You execute a call which is from a sender. Okay. So to using this mechanism usually used in a closed environment, okay, or so the both sender and receiver, they use the same, they are trusted to each other, and this design usually is internal design, so they have a way to make sure that the active message will not crop the receiver side system and so on. Okay, but it's similar to an applet, the browser's applet code. Okay, that similar mechanism, it can be used in message passing also. So you can see from here you will find out that the non-broken receive and non-broken send to support this kind of semantic, the complexity is much higher than support broken send and broken receive. Okay, so depends on what kind of system you are using. Okay, so when you using send and receive system call, you need to figure out the semantic of the system code, what kind of semantic they support. Okay, and make sure you fully understand the semantic. Otherwise, your usage may not fulfill your imagination. Because you find out the result may be different than you expected. Okay. Another message passing mechanism we call it remote procedural calls. Okay, it's a more high-level mechanism on top basic send receive. Okay, and the reason to support this lot is that because it's a procedural call. Okay? Instead of using explicit send receive mechanism, you use procedural call because most programmer application they are very familiar to procedural call. Okay, the meaning of the procedural call. So you try to create an illusion that using the procedural call from one process to call a procedure in another process. Okay, instead of send message, but you use procedure. So the basic idea for that is server the process which expect to receive request message. We call it server. Okay, will export a set of procedures, which that's a set of entry point you can call. Okay, and by the client. Okay, and a client will make a local call to this exported remote procedure. The reason, the mechanism between these two is that after server export this set of procedure calls, then the RPC system will generate a routines we call stop routines. Okay, and these stop routines will be used by any client program. Okay, so any client program if they try to call this particular server, one of the procedure of this particular server, they need to link this stop routines. Okay, so during this stop routine, the procedure call will be transformed to message passing. Okay, so in the client side, they make a local procedure call to the procedures supported by this stop client side stop. Okay, and inside this client side stop of this proxy procedures, we can call it proxy procedures because they are a proxy of this real server side procedures, okay, in the client side. Okay, so inside the client stop, they will create a set of proxy procedures, okay, to represent the server procedure. Okay, so the client, any client program, they need to link this client side stop, so they will get a set of procedures which is a proxy of this real server side procedures, and during these proxy procedures, the only purpose for these proxy procedures in client side is that they will translate this parameter to a message body, and then make a message send request to send to the server, and server eventually will propagate this message to a particular server side procedures. Okay, and waiting there until this server procedure after finish they return, and then the return, the result will be also make up as a message return back to this client side process. Okay, and this client side process eventually will return this local call to the client applications. Okay, so the behavior is something like this. So from the client programming's point of view, it just make a local call. Okay, instead of writing this send, receive, message passing APIs, they just use the procedure call. Okay, and so on. Okay, so that make the programming's life much easier because they don't need to learn how to use this send, receive, network APIs. They use the general purpose procedure calls. Okay. So RPC model is a user procedure call as a process communication mechanism, okay, over an abstracted mechanism to hide how this low-level communication detail. Okay. The purpose of this model is they make remote procedure look like a local procedure. Okay. Of course, the behavior will be a little bit different. Okay, because for local procedure in general, if the system fail, then the whole process fail, right? But here, the client process is running in one machine, the server process is running in another machine. So the procedure may fail, procedure call may fail, but the client process is still active, right? So the behavior, the failure behavior or failure model will be different. Okay? So you need to take care of these failure, different failure semantics and so on. And the issue for this RPC is that how to make sure this low-level communication detail be hidden or encapsulated from the programmer. Okay. The most RPC system they have their own mechanism to support this. Okay. And the parameter passive, because parameter using procedure call, so we need to consider different kind of semantics for parameter passive. Okay. In general, the procedure call you have a pass by value, right? Call by value, call by reference, or call by others. Okay, and so you need to handle that separate. And another one is the how to bind, okay, locate the server. Okay, and if the environment are different, okay, the caller and receiver, their running environment, if they are different, for example, the operation may be different, architecture may be different, then they may be implemented by different language and so on. Okay, so that's heterogeneity, the support. Okay, and another one is how to deal with failures when failure happens. We need to handle. So most RPC systems they need to consider this at least these 5 major issues. Okay, some systems support all of them, and some systems they may only support some of them. Okay, so whenever you use an RPC system, okay, you need to understand. You need to look into detail what kind of how they deal with this. Okay, then when you use and something unexpected happen, then you will be able to know what where is the problem and so on. Okay. In general, the step to make an RPC call will be something like this. Okay. Most of the systems they require 3 modules in both sides: server side, the sender side, and receiver side. Okay. And user application. Okay. Or sometimes we call it client or server program. Depends on it's a sender side or receiver side. Okay. And a set of stub routines. Okay. Client side they have a stub routine okay. And server side they also have a stub routine. Okay. The client side stub is a general message from the parameter and then general message to send to the server. The server side stub will receive the message and then unpack the message to parameters and then call the real procedures. Okay, on behalf of the client. Okay. And waiting for the return. And after they get the return, they will they'll pick this return parameter as a reply message and then send back to client stub. And here the client stub will unpack the reply message and put it to the return parameter for the procedure call. Okay, and so on. So they're doing something like this. And also we need to have an RPC long-term support module. This doing the detail of the communications. Okay, and that's the 3 programs, 3 modules, and you need to link them together so that the client side program and server side program they can work together. And also, the detail of the data flow is something like this. A client program involves a library routine we call client step. Okay. It may contain parameters. Client step generate message to send, and the parameters are marshaled as a message inside the message body. Then send using this kernel, actually using the underlying send and receive mechanism to send a message to server. Okay. The server side kernel will receive the message and then call this server stuff. Okay. The server stuff doing the opposite way. Okay. They involve the server procedure after marshal the message into parameters and so on. Okay. And then after the procedure return, they do it the process will go from here to here. Now it's from the server stuff to the client stuff. So the data flow is something like this. Okay, the client call client stuff by parameters, and then pack those together as a message, and then call underlying system, deliver to the other side system, and then they deliver the message to server stuff. Server stuff unpack the message and then make actual procedure call to the server procedures. So the application programmer doing this part, the work, their program is in this part. The server program also is in this part. This stuff and client stuff and are generated by RPG system or supported by the RPG system. Okay. So after this finish, they go back this way and then back to client. So the communication details are all hidden by these RPG systems. Because the server stuff and client stuff, they need to marshal and unmarshal the message, the parameter to message or message to parameter, okay, and so on. Okay. And this marshalling they need, in general, the activity for this marshalling consists this by order problem, okay, because different data representation they have different mechanics. For example, for ASCII, for character they may have using ASCII code or Unicode or others, okay. And for the integers, they may using big Indian representation or little Indian representation because different CPU they have different way to represent their integers, okay. And also different CPU they have different alignment requirements. Okay. So these are all need to be considered. Okay. So you pick this and translate this to a standard form. And so the receivers, after they receive the message, they will know how to translate from the standard form to their natural form. Natural form means it's natural, it's architectural support. What is the CPU using and the character sense and so on and the alignment. Okay. Okay. So you need to do this transformation between this standard form and the natural form. And for the parameter passing, okay, if you try to pass a pointer, then you need to do something like copy on demand. Okay, you need to copy everything this point. Okay. But however, if the structure, the pointer point is very complex, then this become very difficult. Okay. So usually the pointer can only be passed for primary type data, integer, real, or whatever. It's primary type. Okay. For complex data structure, usually we don't allow passing by pointers. Okay. And also, if the sender is using C to write its program, they make anticipate this unbounded array, okay, because in C they don't check the boundary. Okay. Compiler did not check the boundary. So when you declare, you try to send an array as a parameter, then it becomes difficult because the array, the size of this array can be undefined in compiler time. And also some system calls, okay, but that's the extreme case, okay. For example, printf, they have different number of parameters, okay. So you don't know. So this is just an example to show the difficulty of doing this, to handling parameter parsing, okay. For most systems, they just did not allow this to happen. That's it, okay. You cannot use this unbounded array and unbounded number of parameters in your parameter. And then there's no problem, okay. And also another way is if you try to pass a global variable as a parameter, because the global variable only meaningful for your local process. This is meaningless for the server, okay. So most cases, most systems, they don't allow this to be used. Okay. So in most RPG systems, they only allow parameter parsing by values. Okay. And some systems, they even restrict. Okay, you need to make sure all your parameters are be kept inside a particular structure. Okay, and so if you try to pass multiple parameters, then you declare a structure, and then those parameters are inside there, and these parameters they are all need to be copied by value or whatever. Okay, and then you send the whole structure as a parameter. Okay. Some RPG you will ask for this kind of restrictions. Okay. Failures in RPG, we said it, okay, because there's a different failure model for remote procedures. Okay. For example, if the client staff cannot locate the server, you cannot find out where because the server may crash or whatever, or any reason, the network become partitioned, so it cannot reach the host of the server and so on. Okay. And the reason for this may be server is currently down, and also maybe because the exported procedure code, their interface is different to used, because the server process usually they may have different versions. For example, they have a new version, so and then you still using the old versions client stuff, and then will become mismatched, okay, and so on, okay. And they may anticipate other exceptions, okay. So you cannot locate the server, and also the message, because the RPG code actually has a message passed inside there, right? So the message may get lost, request message may be lost, and also reply message may be lost. Okay. And another possible way is the server may crash after receive the request, but before it can handle, before it can generate reply, it crashed. Okay. And also client may crash after send out a request. Okay. So eventually the server generate response, but cannot reach the client because the client already crashed, and so on. So these are all possible failures. Okay, you will not anticipate in the normal local procedure calls, but in RBC it's possible. Okay, so to handle message lost, okay, either request message lost or reply message lost. Yeah. The way to handle request message is using timer, okay, and resend. Okay. So the sender inside the sender's client side stuff or runtime routine, they can use the timer. So and the timer usually is set to based on the historical result or statistic that the message delay between the round trip delay and the handling will take how much time. So you set a timer which is large enough to cover all these activities, and then it if the time expires, you did not get a response, then you just resend the request message again, and so on. Okay, that's the most common way to handle message loss for request. Again, the prime message can also get lost also. Okay, but you can also use the timer and resend in the client side. Okay, and to make sure the server can distinguish the two requests are the duplication. Okay, so server may need to do something as well. Okay, if the duplicated message can crop the server's data, okay, the semantics, okay, then they need to do something about that, okay, because most of the RPG server functions they may not be idempotent. Idempotent means there's no side effect were generated for this function call. So that means a function you execute one time and multiple times, they always generate a result which not only result is identical, but there's no side effect outside this particular function will be affected. So this kind of function we call it idempotent functions. Okay. For example, this function only doing some mathematical calculation, and this calculation only depends on the input parameters. Okay, so they will not generate any side effect to other variables or other data maintained by the server. Then this function is idempotent. That means if two duplicated messages will not cause any side effect, okay, and as long as those duplicated messages, their parameters are all the same, they will get the same result. Okay, so this kind of function is idempotent. Okay. Mathematically, that's the term. Okay, so one way is that if the server can make sure that all its procedures are idempotent, then they don't need to do anything, right? Only the client side using timer and resend, because the server handle the duplicate message. They don't need to handle because duplicated message will not cause any side effect. However, not all the operation can be defined as identical. For example, for file access, we can using this is a sequential read file or API. So you give a descriptor and a buffer with size, right? For this kind of operation, they will automatically increase the position counter, okay, position pointer after you make a read, and then the pointer will change to according to the size. Will advance n bytes, and then so next read will read the another n bytes. Okay, so to make sure these read are idempotent, then you need to use this kind of interface. Not only the position, not only the size of the byte, number of bytes you want to retrieve, you also need to include the starting position of this n bytes. Okay, then for this kind of interface, this becomes idempotent because this read operation always return the same data content. Okay. As long as this parameter are all exactly the same, they always return the same thing. And because this is the read operation, you will not generate any update to the data maintained by the server. So there's no side effect will generate. So this operation you can be duplicated, tripled. It's no problem. They will not. You always get the same n bytes. But some operation, for example, you deposit, you change updates content of account value balance, then it's impossible to make this operation become idempotent because once you update the balance, the update is update, right? You cannot update it twice. Okay. So for this kind of operation, in most cases, the operation which cannot be redefined as an idempotent usually involve update. Okay, then you need to make sure that the server can distinguish it's a duplicate or not. Okay. And the way to handle duplicate usually that means the request need to have not only sender need to using number and send. Also, they need to embed a sequence number for each request message. So the receiver, when they receive a message, they will keep track of which sequence number is already being handled. And then next time we receive a message, you find out it's the same sequence number from the same sender. Then the receiver will know it will not redo the operation. Will not, okay? It just use the original request, the result of the original request, and then return those results. Okay, it will not try to make the operation twice. Okay? So to handle duplication, usually you can use sequence number in the sending the message. Okay? For no crash, okay, if a process a host crash, okay, one way is that you just do nothing. Okay, make the responsibility become the users. Okay, so the system did not guarantee anything. Okay, so again, when you using an RPC, you need to know if the RPC the RPC system they will take care of this failure or not. Okay. The one most common semantic we call at least once semantics. That means when the sender get the procedural return, successful return, the request is guaranteed executed at least once, either no execution or at least once. Okay. The reason for that is that because if the operation is attempted, that means at least once. Okay, so one or more. Okay, because it may execute multiple times, but because the function is attempted, so there's no side effect generated. Okay, so for this kind of semantic, that means the server can guarantee that you use the resend, the timeout and resend, and the server once it get the request, it just execute its procedure and send back the result. Okay, for each request. Okay, so this kind of mechanism we call it at least once, guarantee the server because you got the result, so server must execute the operation, so you can get the result. But during this communication, the request may lost, reply may lost. Okay, but anyway, eventually you get a successful reply. Okay. Another semantic is at the most once. That means the server guaranteed they only execute this operation at the most once, or not operation, no execution at all. Okay, so usually means that after server crash and recover, request can guarantee either it's already been executed or it's not. Okay, so to support this, server need to be able to handle duplicated message. That means client need to embed a sequence number in the message. Okay. So client will embed a sequence number in each request, and server will accept this request and result. Okay. So server also need to maintain a table, a buffer to keep all these requests, okay, and with its result. Okay. If server need to allocate to record this, then you need to have a way to discard this recorded reply. Okay. In general, the server can discard the result because when it receives a new request from the same client. So, for example, your sequence number is n, you record the n message with its result. Then later you receive the n+1 message. Then you know the client already received your nth reply, so we can discard this nth information about this nth request. Okay. So only the last message server may store there for a long time. Okay. But eventually when this communication between server and client are broken, then server will know this particular client. The information about this particular will no longer be needed. Okay, and so on. Okay. And exactly once, that means it's not at the most one. It's exactly once when the server client receive the guarantee that server execute once. Okay, so that means you need to handle not only the server crash but also the client crash. Okay, each request has a unique secret, and both client and server need to log their request and reply. Okay. The reason for that is that okay, when client may crash also, right? So server can crash, client can crash. Okay, but anyway, so before client send out the message, they would log the sending the message. Okay, and they also log the receive the reply. The server also doing the same thing. Okay, so if the client crash and data recovered, then they will look their log. When they find out there's a message sent but not received the result yet, right? So then client can resend the message. Okay, and if the server may crash, may anticipate crash or not, but anyway, because server has lost record also, so after client recover, they can resend the request. And server will find out this duplication, and then they just send out a recorded result back. Okay. So by using this, you can guarantee that server only execute exactly once. Okay. Okay, let's take a break. The exam one's answer sheet you can take back. And the suggested answer is in the E3 also, okay, and the statistic of the score is also in the E3, so you can check it.
没有拿 A。
有 A 的，就是忘记有没有 E。
然后问第几题
16。
16题，16题是谁？你看。好多啊！那我他
user level 所以会有 context switch。
对啊。
user level 所以会有 context switch。
会啊，会。是如果是user level 错的，如果 process 直接到一个 I/O 的话，它就会变成正常的。那如果是 kernel 错的话，
那你可以讲一下你
它分类是
要不要我解释？
difference 啊，那就
写3个吧。
现在为什么刚才这个不需要或者是要？他们这个局都是 kernel space 的。哇，
你这个叫不叫 context switch？叫 user level 的 switch。你这个答案是有点快的啊，这是不完整啊。所以里面讲的很清楚。context switch
大家会分数吗？大家都会分数满意。
啊，对，下次我们再改。我们有公告，他们如果有问题，他们就会来找你了。今天才公告答案，所以他们不知道啊。因为我老二就讲啊，然后还有一点是可以，就是照着
不是大家是不会
可以啊，就在上面再这个，然后题目上面再把这个讲一下。
大家都有放在那个
尽量写的工整，用那个标楷体写正楷，正楷，就说啊，你说有的英文对吧？这个英文，真的我们那时候改到有点不知道到底在改，越改越难。没有，你就叫他来，再通知他。你下次有时候你就把那段影印起来，email 给那个人，说你这一段要不要写出来？啊，你就上来，对。因为我们在还没公布它之前，都可以做这个事情。所以说第一件先 scan 一下，如果发现不是很关，抱歉。因为对工程的定义都不一样，对不对？你这样他写工程，他还会有一些比较潦草。当然，你在上面有讲会比较好一点。技术是还好，不算太长。你是技术是平均嘛？对，技术是平均，对。是平均的，对，那 median 中位数的。算这样。标准太难。对，看一下中位数。然后现在消息上面。
所以就要记得。 帮我记一下。
我加错了。
对，那个80，你记一下，因为我带错。来，我聊。
我想确认一下，问一下一姐。
知道呀，是谁讲的？不知道。他一样，就把你要问
第7题。
我的。
就像我想问，就是跟你这个定义写，我想说只要写到，
可是应该是还是要写到，就是说你用那个，
说要 disk swap 之类的。
对，然后你是增加实体记忆体空间的。
你是要问？
因为你可以用 swap 的方式，那你就变成整个可供记忆不再是具备实际的 memory 空间，这是后面 storage
对，
逻辑上可见的。所以我就没有给你全部的数这样子。对，大概是这样子。
哦，因为你要说少一个，就是它会因为咨询的顺序不同，没有几次要这个，就单位咨询的。你前面有这个有系统的税去竞争同一个学美动这样资源，可是后面再少一个，就是因为它会因为执行的顺序不同，它会有不同的结果。这个就是为什么？对，
至少一个。
你家会认得谁？
我都会写跟 order 有关系。
对。所以你分别16。
Okay. Let's continue. If you have any question, you can go to the lab to discuss with the TAs. Okay. We are talking about the message passing, okay, send and receive primitive, okay, and then we have discussed the remote procedure calls, which is a high-level mechanism for message passing. Okay. The reason to doing message passing is that the information is well defined by and managed for the exchange. Okay. However, because we discussed the shared memory mechanism in multi-processor system, they have actual real memory shared, right? And for those kind of parallel program, they are written by using shared memory mechanisms. Okay, when the system scale up to multi-computer, then the original written application codes, those using shared memory model, okay, or shared memory programs. Now you need to rewrite by using either RPC or message pass or send receive primitive. Okay, so that costs a lot of effort to rewrite those application programs. Okay, so there's a mechanism we call distributed shared memory, okay, that was proposed. That means it tried to create an illusion of a shared memory in this multi-computer environment, okay, such that the original written by using this shared variables mechanism and the code written for this can be ported to this kind of multi-computer environments. Okay, so that's the reason at least especially in early 1990s. Okay, because in that time this multi-computer become very popular. So and before that we have a multi-processor system. Okay, so another code is already written for these shared variables, and when we find out when you want to scale up to incorporate more processors, then eventually we have this multi-computer architectures, but the drawback for that is that the code you need to be rewritten because now there's no shared memory. Okay, so you cannot use this mechanism to exchange information by shared variables. Okay, so that's why some of the scholars, or especially in that time during the early age of the multi-computer systems, so then there's a distributed shared memory middleware or distributed shared memory facilities were proposed, and a lot of research doing this, okay, to support this illusion of the shared memory. Then, so the original written applications can be ported. Okay. So a method allows process on different computers to share regions of virtual memory. Okay, and we call it distributed shared memory. Okay, especially and the implementation of this usually is an extension of traditional paging systems. Okay, because the paging system uses a virtual memory mechanism, right? You virtualize your memory space, so their user's memory space can be larger than the physical memory. Okay? But because the pages can be stored in physical memory or in disk. Okay? In here, the pages can be stored in your local memory or in other computers' memory. Okay? It's similar things. Okay? Only difference is that paging can be either in your memory or in other computers' memory or in disk or even in other computers' disk. Okay. Anyway, okay, it's still a paging system. Okay. So most implementation of this DSM, they just using the extension of the paging. Okay. So they can cooperate or combine into the virtual memory mechanism of traditional operating systems, okay, and they extend that. Okay. So the backing file is globally accessible. Okay. And this globally accessible can be in the globally shared disk or other computers' memory. Okay. And also, read-only pages can maybe replicated, okay, if needed, or writable pages it can be management by either. It's very similar to cache. Okay, in multiprocessor system we use the cache coherent protocol to manage to make the consistency of this duplicated caches or whatever. But here the duplication is in page level. Okay, the only difference is the granularity is much larger. Okay, in the cache line usually is 64 byte or even 128 bytes. Okay, but in that side, in that granularity. But in paging, usually the page size is 4K or 8K or even larger. Okay, so the difference is the granularity. Okay, but the mechanism will be similar. Okay, for a page which can be updated, we call it writable pages, can be mentioned by either single copy only. So that means the system only contains a page which is writable in some particular machine's memory. Okay. So usually it's the last writer. Last writer will keep the writable page. And of course, for writable page, you can also use a multiple copies mechanism. Okay, and the way to do that is that initially you let all the pages are read-only, but when you try to write something, you get a global lock for that. Okay, and the way to do that is you invalidate other copies except yourself's copy, and then you write to the local copy, and after that you propagate to other copies. Okay, so after write, your update will be propagated to other embedded copies, and then make those embedded copies become validated also. And but the status of this page become read-only again. Okay, so that's nature or general way to handle this. Okay. We are not going to detail to discuss the mechanism, okay? Because right now most systems they were not using the DSM at all, okay? Because right now the multi-computer system, because these old codes written by shared memory, most of them are already been upgraded, written by either RPC or censorship mechanisms. So it's become useless for this DSM also. Okay, but it's still there's some academic work to discuss this distribution memory. Okay, also. The pages of this virtual memory, okay, so remember the DSM is a kind of virtual memory, okay, or it's a virtual extended virtual memory, right? Distributed among, for example, we have a full machine, okay, and if the system support single copy only, that means you always, every copy, writable copy, only one, okay, one writable. If the page 10 initially is in this CPU 1, okay, or machine 1, and then referenced by CPU 2. Then for this single copy mechanism, the CPU 1 will be copied to CPU 2, okay, after the reference. Okay, so that's easy. Okay, whenever a computer try to reference a particular page which is shared. Okay, here the virtual memory here, the distributed shared memory only used for shared pages. Okay, for those processes they don't share anything with other processes. They don't need to use this facility. Okay, so only those shared pages. Okay, then you incorporate this part. Okay, also so only those shared pages they are dispatched or dispersed among those physical memories, okay, across the machines and so on. Okay. So that's the single copy mechanism. But if the system support multiple copy, then the same thing. When CPU 10, CPU 0 try to access page 10, then page 10 will be copied to CPU 0. As long as this access is the read access, then it is allowed to make another copy. So, okay. So to make sure this consistency of these virtual memories, okay, you need to have a similar the coherence protocol, very similar to that, to make sure. Okay. So data in shared address space, okay, remember, is accessed as the virtual memory of the central system. Okay, so we need to have a mapping manager, okay, inside the operating system to track, map the shared address space to this physically dispersed memories. Okay, and by using this, if the data structure, the shared data structure is complex, then still be able to using pass by reference. Okay, because inside your program you still have a procedural codes. Okay, and this procedural code they can still use, because as long as those data are in this shared address space, okay, then it's all right. Okay, and paging over network also the locality and other normal virtual memory behavior or property will still be captured in this environment. Okay, and the most beneficial things for this DSM is that now all those written for multiprocessor system become portable, okay, to this larger or scaling multi-computers. Okay, you don't need to rewrite those codes. Okay, you just doing the recompile. Okay, because for this DSM, if in the multi-computer system, if they support DSM, then the compiler need to know that. So for those compiler, you use this shared variable. They can automatically map those shared variable to this shared virtual memory space. Okay, and so those codes can be useful. Like you don't need to rewrite. Okay. To implement the DSM, okay, usually because this, as we said, is a virtual memory, extended virtual memory. So operation hide the fact the page may reside in memory or disk, or in this case, in other machines' memory. Okay. So in multiprocessor system, only a single shared memory module, okay, accessible by all the CPUs. Okay. So it's possible you have multiple caches and so on. Okay. But in DSM, shared data is also can be accessible for all the machines. Okay. So each machine has its own random access memory, but this virtual memory is shared. So page can be physically in any random memory or on disk. Okay, the disk is still available in there. Okay? So the location of this shared data must be kept. Okay, so usually you need to have a memory mapping or mapping manager to keep all this virtual memory to recall the information of this. So whenever you have a page 4, okay, so here, if a system supports this DSM, then the page 4 you need to avoid to distinguish is a local memory page 4 or shared memory page 4, okay? Because only shared address space you will go to this DSM. For nature, local, your processes are non-shared address space. You may also have a page 4 also, because the operation, if they support a paging, then not only for those shared space, for non-shared space, you also using paging. Okay, so page 4 you need to distinguish is in the shared space or in the non-shared space. Okay, either way, you have different way to handle that. Okay? So operating system can fetch the page from the remote. Okay, so and this memory communication delay and coherent protocol must be lost. You have this overhead. So the most important thing for implementing DSM is try to minimize this overhead. Okay, so different implementation, they're using different mechanisms to minimize this part. Okay? And the implementation of DSM usually you can implement in 3 different ways. Okay, place layers. For example, you can implement it on top of the hardware before the operating system. Okay. In this way, then if we implement in this layer, then operating system, even operation don't see the shared memory part. Okay. So this kind of implementation usually we call it hardware implementation. Okay. So you implement this DSM facility in this interconnection network layer, usually in there. Okay. So the operating system will map some of the memory to that part, especially for the shared memory to that part, and those parts are handled by hardware. Okay, so operation they don't need to know that. Okay, but for this kind of implement, usually is in a closed environment. That means all these nodes they are in the same organization, and they are within usually is within a cabinet, okay, or whatever, those kind of system. Okay, and the second layer is on top of the operating system. So operating system support this part. So it is usually is as a virtual memory extension. Is this kind of implementation. So application and the runtime system, whenever they use the shared space, they will go to there. Okay, it's part of the virtual memory of the operating system. And also some implementation is on top of the runtime, so it's in application layer. Okay, That means the application need to be recompiled in some way, like those shared memory, shared variables or shared data structure. They will be handled by this application layer mechanism. Okay. So you can implement in these 3 layers. They have different difficulty for the implementation of this. Okay. So some of the detail of this is that in DSM implementation, every computer they have their own page table. Okay, and if access page is not in the local, then the message will send to look up where the page is. Okay, and the page then will be fetched. So we need to have a lookup algorithm to locate the page. Okay, and then you need to have a migration algorithm for page to move the page to your local. Okay, and so on. So, and as we mentioned, some replication may be used to reduce the traffic. Okay, so there are 2 policies. One is re-replication. Okay, if the page is read-only, then you can replicate. Okay, it's similar to cache coherence. Okay, in the multiprocessor system. Okay, so if a page is readable, is re-replication, then they need to be set as read-only. Okay, so other copied must. If you try to write, then you need to embed it. Okay, first. So another way is you not only allow replicate, you allow all pages to be replicated. Okay. Then you need to have a global lock mechanism. Okay. So for those writable pages, okay, they have multiple copies in different machines. Then before you doing actual update, you need to get a lock, acquire lock before you doing the write. And when releasing the lock, usually this acquire lock, whenever a node acquire lock, write lock, and he got the lock, then he can update his local pages. Okay, and after finish this update, you need to release the lock. Okay, and during the release phase, the changes can now be propagated to all the other copies. Okay, so after this finish, then the lock really released. Then the other write request can be performed. Because may have several write requests pending there. Then those write requests they will acquire, they will compete for this write lock. Okay, anyone get the write lock, then it can update its local pages. Because now all these pages they are already consistent, because during the release lock phase, they guarantee the propagation will be complete and successful. So that's in general the mechanism used for the DSM to implement, to enforce this consistency. Okay. But the DSM has because the size of the page may make this problem become non-tolerable. For example, okay, there are some situations we call it forced sharing. Okay, because if this page are shared, okay, but these 2 processes they all, although those variables they are shared, okay, but in some situation, for example, this process right now is asking for this variable A, and this process is asking for variable B. Okay, although A and B are shared variables, okay, but unfortunately they reside in the same page. So if even they did not access the same data simultaneously, but because they are in the same page, so this page need to be handled. Okay, they cannot be doing the write simultaneously. They need to doing the update or write operation sequentially. Okay, so this we call it forced sharing. Okay, so you can see that if this page, the size of the page, we increase the size, then the force sharing, the opportunity for force sharing happen become larger. Okay. So that's what the decision for the size of the page will influence the opportunity. Okay, for this situation to happen. Okay. So in general, we need to have a good compiler. Okay, which can try to reduce this. Okay, but it's very difficult. Okay, because theoretically it's possible, but it's very difficult to do that because you never know in the long term. Okay, because you cannot assume, you cannot make any assumption about the behavior or the running speed of this program run in different process, in different machines. Okay, you never know when this will happen. Okay. So that's always the problem for this force sharing. Okay, theoretically they should be able to doing the right operation simultaneously. Okay, because they are updating the different variables, right? But unfortunately, these variables they are in the same shared page. So for the consistent handling reason, they need to be written serialized. They need to theoretically written. Okay, so that's the you cannot totally avoid that. Okay, but there's always an opportunity for this. Okay. The scheduling for multi-computers, okay, now become a little bit complex than the multi-processors. But in other ways, they maybe the complex. That means if you try to get an optimal scheduling, it is almost impossible because there's no global state exists because everybody is independently handling their local resources. The only thing those computers they can exchange their state is through the network, right? So it's very difficult, and there's always a delay between these messages. So it's possible to have a global state or the spontaneous global state. It's impossible for that. Okay, so you cannot make the optimized decision, okay, anymore. Okay, so the most systems will try to make sure that after schedule these processes, all the computers they will have almost equal loads. Okay, so you will try to avoid the situation that some computer is heavily loaded and some computer there's no job is running there. Okay, you try to avoid that. Okay, that's the only natural requirement. Okay, for this scheduling in multi-computers. Okay. So in multi-process system, if we have a shared, because you have a shared memory, so you can have a shared ready queue. Okay, so a CPU always can find out some ready process, even from this shared ready queue or from its own ready queue and so on. Okay, but in here, multi-computer there's no physical shared memory. Each node would have its own scheduler, own ready queue. Okay, so usually when a new process is created, you will assign to a particular node in the creation time. In most cases, the process will be created in its parent host. Okay, which process create this new process? Then the process will create in there. Okay, because remember in Linux or in Unix, like using fork during the system called fork, the new process will be created, right? But in the beginning, they'll copy everything, okay, inherited everything of each parent, and those states are in the memory of that particular computer. Okay. So it's natural you create your child process in the same machine. Okay. It's much easier. Okay. And in multi-computers, most cases, the process will stay there until it finishes. Okay. However, because this low latency requirement. So we try to make sure that all the nodes are used almost the same in the same way. Okay, they have a similar load. Okay, so it's possible because this low latency, you create a new process instead of in your local site, but you create a new process in other machines. Okay, it's possible. If your local machine is heavily loaded, okay, then you may create a new process in the more machine. Okay. So if we have a coordinator, okay, in this system, okay, then it's possible this game scheduling in multi-processor system can be used for this multi-computer system as well. Okay, because if you assign a particular node running this coordinator protocol there, algorithm there, okay, so whenever you have a process, a task comes in, you know this task eventually will become, for example, you require 10 process, okay? Then it's possible you use the coordinator to assign this task into 10 10 nodes, okay, simultaneously, okay, and so on, okay. So you can use this game scheduling mechanism, okay. And now the next thing you need to take care is that those process, they need to be start and finish for each time slot synchronized, and it is not easy in the multi-computer systems, okay, because every computer would have its own clock, right? And you need to have some kind of synchronized clock first, and then you can do some synchronized time slot, okay, as well. So to support this, again, we need to have a tightly synchronized clock for those computers. So it's possible using this game scheduling. So that's just if you try to use the mechanism developed for multi-processor system in this multi-computer. Okay, game schedule is one possibility, but you need to first have a synchronized clock. Okay, and so to make sure the load of those multi-computers are almost even. Okay. Then one particular algorithm was developed for this multi-computer system. We call it processor allocation algorithms. Okay, and the optimization the criteria for this algorithm is that assume, okay, that every process would we would know that its CPU requirement and memory requirement. And also, we know the traffic communication between any pair of processes. So this schedule is used to schedule cooperated processes. For independent processes, you don't care about that because there is no communication between them. Okay, so this processor allocation algorithm is only used for cooperated processes. Okay, so cooperative process, here we say you can use game scheduling. Okay, directly you migrate this game scheduling from MP to these multi-computers, or you can use this specific for multi-computer, designed for multi-computers. Okay, but you need to know, you need to have this assumed value, okay, estimated value for CPU, time, and memory requirement, and also traffic communication bandwidth requirement between any pair of processes. Okay, so if we have this, then it's possible to achieve a global goal, minimize the goal or optimal goal for this. Okay, and the goal for this usually is try to minimize wasted CPU cycles. Okay, you will try to run this algorithm, this whole set of cooperative process, okay, finish them as soon as possible, or reduce their total latencies, okay? And you also try to minimize the total communication bandwidth used for this, okay? And another thing is ensure the fairness of the process, okay? The load of this process, computers, you try to make sure they are as fair as possible, okay, for users and processes, okay? That means all the GPUs, they are used okay, in the equally way, loaded way, okay? So we assume this, and it is possible it can derive. And here we give a simple algorithm for this. We call it deterministic process allocation algorithm. Deterministic means you know everything beforehand, okay? Assume we know CPU and memory requirement for each process and know the traffic between any pair of, and a system is represented. Why? Okay. Then the whole system we can represent as a weighted graph. Okay. In here, every vertex represents a process. Edge between these nodes we represent the traffic requirement between these two processes. Okay. Then this PA process allocation algorithm is used to reduce, to find an effective way to cut the graph, okay, into k-disjoint subgraph, okay, and this with some constraints, okay. So each feasible solution, the edges among the subgraph, okay, represent the real network traffic, okay. So the goal is to find a feasible solution which minimizes the network traffic. Okay. So you find a disjoint cut. Okay, you cut the system into k subgraph. So only the edges close to this subgraph will become the real network traffic. So each subgraph represent those processes will be assigned to the same machine. Okay. So by doing this, we call minimum cut algorithms. Okay, so actually you transfer this PA algorithm to a minimum cut algorithm network or graph, the minimum cut algorithms. Okay, and the K represent, if you have a K computer, it's free, right? So you cut, okay, this to K set, okay? And as long as the traffic among this K subgraph are minimized, okay, then you can get a feasible solution. Okay. Then here's two feasible partition. Okay, for example, we have this graph represent a cooperative process. Okay, and this process have 9 processes. Okay, and these edges are their traffic pattern, okay, traffic bandwidth requirement. Okay, and one minimum cut is that we can cut this. For example, if you have 3 computers are available, right? Then you will cut this to 3 parts. Okay, okay. This is one way, and this is another way. Okay, so for this, we have 30 units of network traffic, but here you have 28 units of network traffic. So eventually, to find out the minimum cut, this one will be the winner. Okay, you check this. Okay, and you assign this cut in one process, and this one to another machine. So we have 3 machines, and each machine has running 3 processes. And here, this cut, okay, this machine runs 3 processes, but this machine need to execute 4 processes, and then this execute 2 processes. Okay, so these are 2 feasible solutions. Okay, they cut this graph into 3 parts. Okay, this one is less network traffic. However, the total latency in here we did not say specify the CPU requirement. Okay, but actually this if we want to consider the CPU requirement also, then it's possible this one has more CPU requirement, so the latency of this one may be longer. Okay, so it depends on your optimization criteria. Okay, the network traffic is much important, or the CPU latency is much important. So it can stack different set of different feasible solutions. Okay, and so on. Okay, or maybe you have you may use a weighted algorithm. So you give this latency of CPU a particular way, and network traffic a particular way. Then you combine them together, make you optimize this weighted summation or whatever. Okay, that's also. So basically, the algorithm is something like this. Okay, you use the minimum cut algorithm to find out feasible solution, and then depends on your criteria. Okay, if your criterion is the network traffic, then this one will be your solution. If your criterion is balance load, then maybe this one will be your solution. Okay. Besides this PA, the problem for this is that we need to have this estimated value. Okay. So usually this algorithm only useful for those application which has running history. Okay, there's a past running history, and then you record everything. Then you can use this for next time you try to run this application, you get a better performance for that. Okay, but if there's a new process coming in, you have no way to do that. Okay, so there's a limitation for this deterministic PA algorithm. Okay. Therefore, most systems they will use this heuristic low balancing algorithm in the beginning for when the new process was created. Okay, and before we have any knowledge about that, then we try to do something about the low balancing. Okay, and also you see the problem if the n is very huge. Usually it's theoretic is a MBR problem. So you can only use greedy to find out a feasible solution. Okay. And dynamic adjustment mechanism for low balancing. Usually we have these two major classification. One is we call sender initiated scheme. Another one is receiver initiated scheme. Okay. The name stands for its policies. Okay. Sender initiator means when a new process created, it always assigned to a node which created. Okay, that's default. Okay, then if the node is already overloaded, then that particular node try to find other place to help. Okay, you probe others, and when receive this probe request, every node will check its load. If you find out it's underloaded, of course, now we need to have two threshold to specify what is overloaded, what is underloaded. Okay, this value. Then you find out it is. Then you accept the probe. You will response the probe, and the creator of this new process will now migrate this process to this receiver. Okay, so that's why we call it sender initiate. Okay, the processor try to send out a process. A processor try to send out a process will initiate the operation. Okay. The receiver initiate scheme is in the reverse way. That means whenever a node find out its current node is underloaded, okay, then it try to ask for more jobs. Okay, it probe others to more job process. Okay, when receive this probe, if a node find out it is overloaded, then it can migrate some of its process to this probing node. Okay, that's why we call it receiver initiation. So a node try to receive process, initiate this action. Okay, and that's conceptually this. Okay, so but the algorithm usually work something like this. Okay, but this is just one variation. You have a lot of variation for this sender initiate. Okay, so again, the principle is the same. Process always created in the the node which create. Okay, then if it's overload, then it probe. Okay, and this probe it can be randomly probe or designated probe by some designated order. Okay, it depends on your implementation. It's all right. Okay, if the probe node is under load, it accept. Okay, otherwise the probe node will repeatedly probe. Okay, so this implementation or this upgrade, this variation is that you probe one at a time. Okay, and set a maximum limit, maximize n. So after you probe n times and no one want to receive your job, then you just create this process in your current node. Okay, that's it. Okay, because the system may be heavily loaded, or every node are heavily loaded, so no one can accept a new job. Okay, so again, because if this situation happens, that means the system is heavily loaded. But the system is already heavily loaded, so this probe message will increase the system load also. So you see, so this particular mechanism, center initiate, when the system is already heavily loaded, you will waste a lot of bandwidth to doing this probing and without any good effect, right? After n times of probe, send out n message and then get nothing. You still need to run the process in your own. So you waste this n probe message. You make the system already heavily loaded become even worse. Okay, so that's the problem for this center initiation. Okay, but if the system is not heavily loaded, then this center initiation is alright because you did not increase too much load. Okay, so that's the only problem. So if the system already in this situation, then this problem will make the situation even worse. Okay, now let's see the receiver initiation. Means when the process finish. So the time for the problem is whenever you finish your job, then you check your current node, right? If you have something to do, you will not do. You don't need to check, right? Some job finish, then you check your current node, okay? Because the current node may be set to be the number of the ready queues, okay? How many processes in the ready queue? Maybe you set. If the number is too small, then you try to get more job. Okay, for example, okay, depends on your system setup configuration. Okay, you maybe use the number of process in the ready queue as load, or you use other factor as your load. Okay, but anyway, usually we generate a problem is when a process finished. Okay, then you do something this. You check its load. If it's under load, then you try probe. Okay. Again, this variation you sequentially probe. You probe someone. If someone return, say, okay, I have something I want to send out. Then you get the process. If no one is willing to give up some process, then after this maximum, that you just continue your work. Okay. But you will see that this receiver initiator will not affect the system load, especially when the system is highly loaded. Then everybody will welcome this problem, right? And usually during the first problem, the node will immediately respond. Will send out because if the system is already in a heavy loaded situation, so it's very easy to probe a node which has job to give away. Okay, so the performance of this receiver initiation will perform very well because whenever you have someone become underloaded, start to probe, everybody will welcome this kind of probing and they will try to send out their job. Okay, so it will not increase the load of the system because it actually balancing the load. Okay. So it will not degrade the performance in heavy loaded situation. Okay. So that's why most of the current implementation they most of the variation right now, they combine these two together, okay? In some sense. Okay? So when a node finish the job and find out it is underloaded, then it will actively probe some job. And when a node create a new process, it find out itself is heavy loaded, it also probe. Okay, so you can combine these two together. These two algorithms will not conflict with each other because their criteria are different. Okay, and their initiation situation, okay, can be coexisted. Okay, because every node will find out that if they have different load situation, then the system may have several nodes levels as a sender, and several nodes is parallel receivers load simultaneously. It can happen, right? So you can combine these two together. Okay. Here we will give an example of the architecture of these multi-computer systems. Okay, we call it cluster systems. Okay, this a cluster usually consists of a set of tightly connected computers. Here we use this word tightly. That means you control your global management system to manage the whole computers. Okay, and let they work together and appear to the outside as a single system to user and applications. Okay, and this computer usually connected through fast local network. Okay, and they have their own CPU, memory, and some maybe I/O facility. Okay, and also may have their own operating systems. Okay, okay. And because these processors they cannot directly access the memory or other, so you only use machine passing, okay, to communicate with each other. Okay. And in general, this system they may share nothing, share no disk or share disk. Okay, so they may have a common shared disk, everybody can access, or without that, so everyone has its own local disk. Okay, so in general, the cluster may be either this shared nothing, so everyone has its own local disk, CPU, and memory. Okay, and connected by a high speed, then or with this, and there's a special I/O node. Okay, I/O host. There's a big shared disk. Okay, in here, and so everybody can access this shared disk. Okay, so typical cluster, something like this. Okay, and to management the whole set of resources. Okay, you can design your own algorithm to manage this cluster. Okay, but here we will introduce this special cluster called Beowulf clusters. It's designed by this gentleman, Donald Baker. He is working in NASA in that time in 1994. Okay, he assembled this cluster by using offshore computers. Okay, so it did not create its own computer, but buy a computer from the market and put them together. So a set of offshore computer connected through a LAN. Okay, and in this cluster, there are two types of nodes. One is a master computer used to interact with users and outside world. So user only see this master. Okay, the other computers are behind the scene. Okay, so a group of slave computers, they did not communicate with outside world. Okay, and a task whenever a task is submitted to this master node, okay, by users, then the master computer then will try to break this task into small tasks, okay, and send each sub-task to a separate slave computers. When a slave finishes its assigned task, okay, the master will send another subtask. So the master doing all the schedule, okay, and partition works. Whenever you generate a task or create a task, the task will send to the master. And master will have a way to partition this task into small tasks and then send task to the step computers. Whenever a step can finish its current task, it will give a feedback to the master. The master will send out waiting subtask in its waiting list. Okay, so it's doing this to make sure the load are balanced. Okay, because whenever there's something to do, all the task slave will have something to do. Okay, and when slave become free, then master will send a new task to them, and so on. Okay, and for this, and also they use these two mechanisms. Okay, in Beowulf cluster, either MPI or PVM. Okay, these are both developed in 1990s. Okay, the MPI has a lot of versions right now. Okay, they still used today. Okay, PVM become more like outdated. Okay, so and the topology of this Beowulf is something like this. Okay, you have a private LAN, okay, and the master is connected to the internet, and these are all connected by this private LAN. Okay, so outside world only see the master. And more about this, you can find out these resources from these references. Okay, and there are many more new references as well. Okay, but those are some of the official sites of this. Okay, so we finish this second part of multi-computers. Next week we will discuss distributed systems. Okay.
Research. I think it was 2011. I met a private network without internet. So I didn't connect it to the internet. So just like probably similar to that. There's 4 computers. One is master, 3 are slave. I'm using MPI coming to